Welcome to this explainer. Today, we are diving straight into one of the most absolutely critical shifts happening in the modern energy landscape. You know, for years, green hydrogen has been hyped up as the ultimate clean fuel. I mean, it's basically the holy grail of decarbonization. You consume it and it emits nothing but water. But there's historically been this massive elephant in the room, an incredibly exorbitant price tag. It looked brilliant in a laboratory setting, but it was just a financial nightmare for the real world. Well, guess what? That narrative is changing rapidly, and today we're going to map out exactly how and why that's happening.
45%. That is exactly how much the global cost to produce green hydrogen plummeted between 2020 and 2026. And look, we're not talking about some pie-in-the-sky theoretical projection here. This is a massive, tangible market shift, and it's being driven entirely by aggressive technological advancements and rapidly scaling supply chains.
There is this stubborn old myth that green hydrogen, which, remember, is made using renewable energy, could just never, ever compete economically with fossil fuel-derived gray or blue hydrogen. But the 2026 reality totally shatters that assumption. In regions with the best renewable resources, green hydrogen is now within just 50 cents to $1 per kilogram of reaching true price parity with blue hydrogen. That is an absolute game changer for heavy industry. So, to really understand this economic shift, we'll follow the data through 5 steps. 1. The green hydrogen price tag. 2. The tech driving costs down. 3. The offshore wind advantage. 4. Storage and transport solutions. And finally, 5. The future of clean industry. Let's get right into it. Okay, section 1, the green hydrogen price tag. Let's look under the hood. Let's break down the actual data. There are 3 main cost drivers defining this whole battleground. Number 1 is the electricity itself. Because you're literally using electricity to split water into hydrogen and oxygen, the power bill makes up a whopping 55 to 70% of the total cost. Every $10 change in your megawatt hour pricing drastically shifts your final cost. The second factor is the capacity factor. Electrolyzers are really expensive machines, and to make them economically viable, you have to run them for over 4,000 hours a year. And finally, there's CapEx, or capital expenditure, basically the cost of the hardware itself. And the really great news here, between 2020 and 2026, electrolyzer CapEx was slashed from about $1,500 per kilowatt all the way down to $700. But how exactly are manufacturers cutting those hardware costs in half? Which leads us to section 2, tech driving costs down. Think about it like this. A major roadblock in early electrolyzer tech was a heavy reliance on incredibly expensive precious metals. It was kind of like requiring solid gold parts just to build a standard bicycle engine. But researchers, like those over in Wu's group, have made these stunning breakthroughs in developing platinum-free catalysts. They've actually figured out how to use renewable electricity to separate hydrogen from water without relying on top-tier, exorbitantly priced metals. Stripping platinum completely out of the equation significantly cuts down material costs and makes mass manufacturing way more feasible. But you know, fixing the hardware is still only half the battle. Because remember, electricity is still the biggest cost driver. So let's look at section 3, the offshore wind advantage. To tackle that massive electricity cost, engineers started looking out to the ocean. Now, on the surface, that sounds like an engineer's absolute worst nightmare, right? I mean, why on earth would anyone take highly sensitive electrolysis equipment and just bolt it to a wind turbine in the middle of a harsh, corrosive, salty ocean environment? Well, the genius solution here is direct integration. Hardware testing is already proving out electrolyzer stacks designed to operate directly coupled to a wind turbine, sometimes hundreds of volts above ground. By integrating the hydrogen production right inside the turbine itself, you're capturing the electricity at the very source of generation. And here is where it all clicks together. Once you generate that energy offshore, you still have to bring it back to land. If you try to transmit electricity via subsea power lines, you are facing massive infrastructure costs and serious electrical transmission losses along the way. But if you use that electricity on site at the turbine to make hydrogen, you can just pipe the hydrogen gas directly to shore. It turns out, pushing gas through a pipe is significantly cheaper and far more efficient than transmitting electrons over a subsea cable. The real-world impact of this pipeline versus power line model is just staggering. Extensive modeling shows that if you produce hydrogen onshore using offshore wind electricity, it costs about $3.86 per kilogram. But Producing it directly offshore and piping the gas in drops that cost down to $2.08 per kilogram. That is a massive analytical victory. It's literally a 45% cost reduction simply by changing where the hydrogen is made. But of course, making it cheaply offshore is only step one. What happens when we actually need to ship it globally?
That brings us to Section 4, Storage and Transport Solutions. So, hydrogen is a notoriously tricky gas to handle. To ship it normally, you'd have to freeze it to near absolute zero or put it under immense, dangerous pressure. Enter LOHC, or liquid organic hydrogen carrier. Think of it a bit like carbonating water, but instead of trapping CO2, you are chemically binding the hydrogen to a thermal oil. Suddenly, you aren't dealing with a highly pressurized explosive or a freezing gas anymore. You're dealing with a totally stable liquid that can be stored and transported at normal, everyday temperatures and pressures. This LOHC tech, which is already being deployed in major projects like Germany's Hector plant, allows hydrogen transport to mimic the everyday simplicity of shipping bottled liquids. And the absolute best part, it creates a perfect circular economy. Once the hydrogen is extracted at its destination, that exact same carrier oil is just returned and reused in an infinite loop. It is safe, it's practical, and it's highly efficient. So with production dropping in price and transport logistics solved, who's actually buying this stuff?
Section 5, the future of clean industry. Right now, heavy industry is acting as the massive first mover driving global demand. And that's because they simply cannot decarbonize using standard batteries. It just won't work for them. For instance, refineries in Europe are now legally required by the Renewable Energy Directive to replace their fossil-based gray hydrogen with renewable alternatives. We're seeing green ammonia totally taking off for fertilizers and maritime shipping fuels. In the industrial sector, green steel projects in places like Sweden are already securing binding contracts from manufacturers who are totally willing to pay a premium for carbon-free steel. Even the cement industry, which is responsible for a whopping 8% of global CO2 emissions, is currently piloting hydrogen to replace fossil fuels in their massive kilns. So let's take a step back and just look at the trajectory we are on here. In 2020, we were stuck with high costs and electrolyzer hardware sitting at roughly $1,500 a kilowatt. Today, in 2026, innovations like offshore pipeline synergy and LOHC have pushed the best-in-class projects down toward $2 per kilogram. And looking just over the horizon to 2030, widespread global parity is projected at roughly $1.50 per kilogram. At that price point, green hydrogen universally beats fossil fuels in the best resource regions globally, period. Which leaves us with this final, incredibly provocative thought to consider. We used to look at green hydrogen and say, hey, great idea, but the economics are just bad. But with hardware costs literally halving, offshore synergy completely bypassing the traditional electrical grid, and heavy industry actively writing huge contracts today, is the fossil fuel era ending much, much faster than we originally thought? Well, looking at all this, the data certainly points to yes. Thank you so much for joining me for this explainer. I hope this really helped you structure your understanding of this rapidly accelerating clean energy transition. Keep learning, and I'll catch you next time.